Welcome back to another HVAC Engineering Techie training video. Today's lesson is on HVAC variable volume systems and outside air systems. So this is a little longer course, but it's designed to actually show you all the different kinds of VAV systems, variable volume systems, and those variable volume outside air systems as well. So remember that this channel is all about everything HVAC. We talk about engineering design, construction, equipment, systems, test and balance extensively, controls, efficiency, and performance. This video is designed to help you advance your career. These system videos are good for both tab people, control programmers especially, and other folks want to learn more about the actual system. So remember, before we get started, if you're not already a subscriber, please subscribe. Hit the subscribe button down below and give me a thumbs up button if you would. It costs you nothing. It's absolutely free. It really helps me with Google, so I'd really appreciate if you do that. And let's get started with this video. All right, so now we're going to get into the general operation of the VAV air handling units. Oops, get my cursor in the right place. Maybe it'll work. All right, this is a typical VAV air handler. Of course, air handlers can come in any kind of configuration as you learn and going through constant volume or the basic system video. So this shows a normal draw-through arrangement with a supply fan and return fan and a full economizer section. Doesn't have to have that, but it might. So this is a 3-coil system, which it has basically a cooling coil, a heating coil, and a preheat coil. To be VAV, it doesn't require that. It can be any number. It can be cooling only. It can be all kinds of different coils. And it has a duct system that goes down throughout the space. And in the space is VAV boxes, and these boxes, of course, make the system what it is VAV. So the air comes from the room in the return. Return fan pushes it through the return section, through the into the coils. The supply fan sucks from this plenum section right here through the coils and blows out to these boxes. Now the boxes basically vary the flow to change temperature in the space. That's why it's called variable volume. So really there's not much else. Of course, it has a control system. Control system has more controls than a constant volume system. So each system in the room has a room sensor and a controller on the box that does all the things that this box needs to do. Now, yeah, I've always told people as a control contractor, you would think that the simplest thing on the job would be these VAV boxes. But if you actually look at the program, this is probably the most complicated program of anything in this whole system. It's just because it's written for all the different configurations you could possibly have, but it can be very, very large. So this has a supply air duct pressure sensor, because what happens is these boxes open and close. They change the flow in this main duct. And what happens is this fan will speed up and slow down to maintain this pressure set point. That's what makes it variable volume. So it can slow down if it only has one of these open and the rest are closed. It can slow down to just provide that air for that one box. Of course, it never quite does that. These are all in different positions. And then as this changes flow, this has to change flow. So that's what makes these a little bit different to set up, because the flow goes up and down in these systems to make sure the room load is handled. So instead of starters, we actually have variable frequency drives, variable speed drives on these, so to be able to change the motor speeds. The economizer is exactly the same, except for the fresh air. We'll talk extensively about that later on. And this particular one has a room pressure sensor. Not all of them do, but that helps to keep the room into constant pressure as these flows begin to change. So that's the general operation of a VAV, and all VAVs work that way, but there are some differences, and we'll go through and talk about those differences. The first is the VAV box. There are many kinds of VAV boxes, and we're going to talk about the predominant 3. So a standard VAV box, variable box, varies flows to the control room to control the room temperature. The velocitrol provides pressure independent operation. So right up here is a velocity grid. So it's actually a pitot grid, and it's a tube round grid. And it provides velocity pressure into this controller. And this controller uses that to make the box what we call pressure independent. So if pressure changes upstream, and this didn't have a flow ring, then as this damper is in a fixed position, if this damper was in a position, this increased pressure would would make more air go across the damper and into the room, changing its temperature. Then, of course, the room sensor would sense it and change the damper. So this would always be fluctuating back and forth because of pressure changes. But with this DP ring, it can sense the differential pressure, so it adjusts the damper accordingly, making this pressure independent. The pressure can change all day long, and it won't change the flow of the box. Now, the way these actually work is the room sensor actually connects into the controller, but the controller looks at the pressure flow, the velocity pressure, and it controls the velocity pressure. So the room temperature sensor resets the velocity set point. So if we know if a certain size and it needs 500 CFM, the box is calibrated so it knows exactly what velocity pressure 500 CFM will have. So this controller will maintain that differential pressure, velocity pressure for 500 CFM. And then when the room says it needs more one way or the other, it changes the set point of the velocitrol, thus changing the flow of the box. That's just the way it works. Supply air is variable volume, constant temperature. Hot water or electric reheat coil if heating is desired. So the best way is to put heat downstream of the boxes. If you need reheat, put it there. We'll get into those sequences a little bit better that can operate the hot water one way or the other. You can also get these with the sound attenuators if you think they're too noisy. Shouldn't be too noisy unless they're selected incorrectly. These boxes need to be selected both maximum flow and minimum flow. And the reason is these sensors, normal box can't sense below 0.01 velocity pressure. So if you select a box too large, and when it's at minimum flow, this device can't sense it, it'll hunt. It doesn't know where it's at. So these must be selected so that you're above 0.01 velocity pressure when you're at minimum flow. And then maximum flow just means the box needs to handle maximum flow. To be quite truthful, the minimum set point is more important than the maximum set point. The reason is most boxes hang out around the 60 to 75% place and eventually down around minimum if it's a 30% box, more than it will at 100%. So that's one of the misnomers about sizing boxes. A lot of engineers believe bigger is better, and with sizing boxes, it is not. They need to be sized correctly. So a typical control sequence is the room temperature sensor modulates a VAV damper and a hot water coil valve or electric heater to maintain room temperature. Supply inlet velocity sensor maintains constant flow during inlet pressure changes, making the terminal unit pressure independent. Now we have another kind of box called a series fan box. So a series fan box does exactly the same thing as the other box, but it has a different feature. It has a fan in it right here, and this fan is in series with the cold valve. So this is the regular VAV box valve here. So the supply air comes in this cold valve, and the damper is the same way. It moves, opens and closes it. But now in this one, we have a fan in series. And this means that in series that the fan is always on when the system's in the occupied mode. And this fan comes on and blows a constant volume of air into the room. And it could have a heater, electric heater, or hot water coil. And it's got a filter and an opening to the plenum. So if this fan has more air than this, like if this, say this doesn't need cooling, so this is way down at minimum ventilation position, then the difference between that air is sucked in from the plenum and goes out this way. So you have the air in the room circulating this way with this ventilation air coming in. And of course, as this opens up, if it needs cooling, it just modulates differently. So this air here is variable volume. This air here is variable volume, but this air here is constant volume. That's why we have series boxes, to tell you the truth. So if you have a space on a VAV system that needs a pressure differential and can't vary the flow, then they use a series box, right? So you can actually put a constant volume. Okay, let's look at this. Series variable volume box. Supply fan is on when it's on the occupied mode. Velocity provides pressure independent operation. Uses interior heat from the plenum. So any heat in the plenum, it will use that to heat the space. Fan induces plenum return air when the CFM is greater than the cooling damper CFM, which we just talked about. Supply air is constant volume, variable temperature. Whereas remember, a regular VAV box is variable flow, constant temperature. This is exactly the opposite, because that's what a series box does. So you'll have series boxes on a VAV system where they have a condition that they can't vary the flow. Hot water electric reheater, and you can have a sound actuator if you require it. Its sequence is slightly different. The room temperature sensor modulates the VAV damper in the hot water coil valve to maintain room temperature. Supply inlet velocity sensor maintains constant flow of the air valve during the pressure changes, making the terminal unit pressure independent. Terminal unit fan runs when it is in the occupied mode, providing constant flow of variable temperature to the space. It's really simple flow, but you have to know that this is the kind of box. Now the program here is a special program because it has a fan start-stop on it. And also, and by the way, this is a constant volume fan, so it's not variable flow. So this controller, same controller as the other, but it now uses the sequence inside of it for a series box. Then we have parallel terminal units. Now, parallel terminal units is another fan box like the previous one, but what it does is the fan is here next to this inlet. So what happens with this particular one, this fan is only on when you're in the heating mode. So if you're in a cooling mode, this is a regular VAV box. VAV box butts air to the space, but in the heating mode, this fan comes on, and then this is sucking in, so it's got two different modes of operation. So look at that. A parallel variable volume box. Supply fan is on only when in the occupied heating mode, off when in the cooling mode. The velocitrol provides pressure-independent operation, uses interior heat from the plenum, so it still uses heat of the plenum to heat the space. Fan induces plenum return air when in heating mode, so it's the same as that series box. When the fan is on, it will suck air from the plenum. Supply air is constant volume in heating mode and variable volume in the cooling mode. So this one changes its stripes. It's like a series box in the heating mode and like a cooling box in the cooling mode. So it's a little different box. You can have a reheat coil, of course, and it has a sound trap if desired. Typical control sequence. In cooling mode, the room temperature sensor modulates the VAV damper and hot water coil valve to maintain room temperature. Fan is off. Supply inlet velocity sensor maintains constant flow of the air valve during inlet pressure changes, making the terminal unit pressure independent. In heating mode, the unit fan is on and the hot water coil runs to provide heat. The damper is at minimum position, providing ventilation air. All right, so let's look at the whole system. Let's go back and look at that. So remember, these boxes can be regular VAV boxes, series boxes, or parallel boxes. Doesn't change the system at all. So here's a typical sequence. Now remember, these sequences I'm showing you are what we call regular sequences that you might see on the drawing from the engineer. These are not actually programmed control sequences. A control programmer will have to have a much more complicated sequence. You might have timers in there. You'll have resets in there. You have a lot of things I'm not showing you because this sequence is just trying to tell you basically how the system operates. So there are courses coming that will deal with the exact sequences, but this one is not. This is just typical sequence. The supply and return fan shall run in the outside damper, should be at minimum position anytime the system is in the occupied mode. So these two fans come on, and the outside air damper is at minimum position. Now, on this particular unit, if you noticed it before, I showed a full economizer with a relief damper, a return damper, and an outside air intake damper. But I also have another small damper next to this one called a minimum outside air damper, because we have a special problem with VAV. If you have just these three dampers on a VAV, as the VAV changes flow, the outside air actually varies. So if you have a low pressure here, it's going to induce a little bit of air. If you have higher negative pressure here, it induces a lot of air. So what we do is we normally try to make sure that it has a minimum VAV outside air damper. And then we modulate this, and normally we have a flow meter based on it. And there are many ways to try to control this, but the very best is to put a flow meter on it. So that damper is controlled to the flow meter. And the reason is we have, for ventilation air, it's a constant. We want to have a constant flow of ventilation air, not a variable flow. If you have this damper fixed, it's fixed damper, and these blowers speed up and slow down, then you'll have variable intake air. And that's not going to meet the code or the standard for ventilation air into the space. So what we do is we normally have that damper, and it's slightly different. So we're going to modulate the supply fan to maintain supply duct pressure set point. So the supply fan is, from this pressure sensor, its speed is controlled. Modulate the return air fan speed to track the supply fan speed, offset by the CFM required to maintain building pressure, and modulate the relief outside air and return air dampers to maintain building pressure. Modulate the minimum outside air damper to flow set point. So I don't know if you remember when we talked about economizers on the constant volume trainings video, that we talked about trying to balance this condition between economizer and normal operation, because this was a constant speed fan that requires some talent to get that balance. These are not constants, so we can actually fool with these dampers, which makes it easier. May complicate the sequence a little bit, but it makes it much easier to actually get it in balance. So we're going to set this fan up to do what it needs to do for the supply, and then we're going to have this fan follow this fan with a delta difference in CFM, which equals the outside air requirement. So if this needed 1,000 CFM outside air, we'd set this fan to be 1,000 less than this one and have it track that. Now that's not perfect, but it does. It's the best, easiest sequence to do this. You know, some people will put flow meters on these fans and track through these flow meters, and that's okay. But the problem is they normally try to use some vortex flow meters, and a lot of them are just a little plastic tube around the inlet, the vortex inlet. Those aren't very good. They break, they don't last, and they're not very accurate. Now, if you buy a really good quality vortex flow meter, that's okay. But it's much easier just to set it up to have the VFDs track them, because, you know, and that is prefaced by one condition. These fans have to be the same kind of fan. I mean, you can't put centrifugal fans like this, one here, and then put a propeller fan back here. No, or a vane axial fan won't work. And the reason is because these curves don't follow it. The fan curves don't look alike. We don't care if they're the same size, but we need the curves to look alike. So if this one's at 50 hertz and we want this at 45 hertz, we want them to actually be cognizant on the wheel. And if you have different types of fans, they will not be. So that doesn't actually work too well. Flow meters work better in that case, but I always try to make sure that they have the same type of fans. So the CFM required to maintain building pressure and modulate the relief outside air dampers to maintain building pressure. Okay, so if in this job, we have a building pressure sensor. So as we change this, as the building pressure structure changes, this one can actually start offsetting by more or less outside air and relief air, or if it needs to, it can speed up and slow down the fan. So we will maintain building pressure because we have a sensor here. When you don't have a sensor, you need to during the balance process, you need to watch these to make sure you don't have overrun in that condition. Okay, modulate the hot water valve to maintain the preheat set point temperature of 45 degrees. So this has got that preheat valve in there, measured at the leading side of the cooling coil. If the cooling coil outlet temperature drops below 38 degrees, stop all fans, close the relief and outside air dampers, and open the reheat coil and chill water coil to 100% flow and send a freeze alarm. So that's just basically running this preheat coil. So what happens if there's cold air coming in here, this coil will heat it up to 45 degrees. And we'll use this sensor to control that. And the reason we can do that is because this coil's set point is normally above 55 degrees. 55 degrees or above. So that means that these two coils can work together with that sensor without a problem. And then, of course, then after that, modulate the chill water and hot water valve to maintain the supply air temperature set point. So we have a supply air temperature sensor here, and it will modulate these two coils to maintain whatever set point we need. Now, a lot of VAVs don't actually have a heating coil. They let the reheat coils pick that up down here. But there is a special condition with those. And that is, if you don't have heating in this system at all, you just have a cooling coil, you have reheat coils on most of these boxes, but you have some that are interior boxes that don't have a perimeter load, so they don't really need heat. So what happens here is if you have this one without a heating coil, and if this air is 55 degrees, or say it's been reset up to 60 degrees, it still may overcool these boxes without heaters because they have a minimum ventilation set point. In other words, that damper is not closed. It's slightly open to give ventilation air to the occupants. So that when the air handler doesn't have heat, it requires a special reset sequence. So, and then this is the economizer. If the outside air temperature is between 45 and 70, the outside air temperature is 10 degrees below the return air temperature, enter the economizer mode and modulate the outside air relief and return air dampers to maintain the supply air temperature set point at the mixed air temperature sensor, which is this one right here. If the outside air return air temp are equal, return to the normal operating mode. Reset the supply air temperature set point based upon the connected load. Every 5 minutes, if any box damper is greater than 95% open and no box is less than minimum position, so in other words, if there's no boxes at minimum position, then lower set point 1 degrees. If no box damper is greater than 90% open and one or more boxes at the minimum position, raise the set point 1 degrees. Reset range should be 55 to 70 degrees. So this is trying to not overcool these spaces. The only problem with this sequence, and this is a real simple sequence, when we do the control course, we'll use the ASHRAE guideline 36 sequence, which is very, very complicated. One of the problems here is if you have a rogue box, it can drive the sequence. So let's say you have a box that's broken or a box that's not balanced correctly. It can drive the sequence where you don't want it to be. So you have to remove those boxes, and you can do it manually or you can do it automatically. Manually is nice. I could just run a report every week and tell you if there's any box, tell me what the percent open of all the boxes are. And if you got one box somewhere that's always 95%, it's got something wrong. You need to fix it, or at least take it out of the sequence loop because it will drive the sequence, and we don't want that to happen. If the room humidity writes, okay, this air handler has a cooling coil and a heating coils, and it's got some reheat coils downstream. So we can dehumidify that. You can also dehumidify if one has heaters on all boxes, then you can use those for reheat. The only warning is those reheat coils need to be large enough to do the reheat when you're in dehumidification mode. So if the room humidity rises above 60%, place the cooling coil in dehumidification mode. When the room humidity drops below 45, return to normal temperature control mode. In dehumidification mode, modulate the chill water valve to maintain 55-degree leaving temperature and modulate the hot water valve to maintain room temperature. Monitor all unit temps, supply air, return air fan status. So this is a pretty good unit. It's a pretty good sequence of controls. Okay, now we have a system called a dual duct. Now remember in the constant volume section, I hope you've already taken that video, it talked about dual duct systems, and this is exactly the same except it has variable volume. So if you'll notice, this is just like the other one. It's got the economizer section, the return fan, the filter section, but now instead of one fan with two coils, it has two fans. So it has a fan for the hot deck and a fan for the cold deck. And remember, this little dotted line represents a blast plate, which prevents a velocity jet from entering this coil and causing velocity jets and heat transfer problems. So these are just to disrupt the velocity and make it go around, so it'll have an even velocity on the whole coil. So it has a cooling coil, it has a heating coil, and this is a hot deck and this is a cold deck. And of course, these are fans that associate with each one of them. And then it has two duct systems. It has a cold duct system that runs in the space and a hot duct system that runs in the space. And every space has these dual duct boxes, has one box for the cooling and one box for the heating. And basically they operate opposite each other. So if the one box is open, the other is closed, or anywhere in between, and they provide this mixed air to the space. So they're able to do that. And they, of course, everything has a control system here. In this control system, we have room sensors. And these sensors are temperature sensors and humidity sensors. So they can sense what it is now. Not all of them have to be humidity sensors, but it's good practice to do that. We have two supply duct pressure sensors that run each fan. We have one on the cooling deck that runs this fan. One on the heating deck that runs this fan. Each of these have their own VFD, and then the return fan has a VFD. And we have a room pressure monitor, just like the other one. Now here we show, and on the other one also, I had a return air temperature here and supply air temperature sensors here. And remember, these are dry bulb sensors, so these economizers I'm showing you are dry bulb economizers. You can use enthalpy economizers where we have a regular temperature sensor and a humidity sensor. And we have normally humidity in on supply ducts also. And then we can run this on, and we have outside air enthalpy. We can run it on enthalpy instead of sensible heat. Now what that does is that allows you to run time a little bit longer because we're looking at enthalpy. Remember that enthalpy is the total heat of the air, where these normal temperature sensors are just looking at dry bulb temperature. So you will miss days that you could have transferred a little more heat in an enthalpy. But enthalpy economizers have a little issue, and that is the stability of humidity sensors. Humidity sensors go out of calibration much quicker than a dry bulb temperature sensor. So we tend to have problems with we have problems with economizers in general staying operable, but the enthalpy ones are much more difficult to stay operable. Okay, here's a typical dual duct VAV box. Now, before DDC became prevalent, we had pneumatic controls, and in a pneumatic dual duct box, it had two dampers, had one shaft that went through these boxes. The dampers were horizontal, and the shaft went through, and it had one pneumatic actuator on the shaft, and it ran both dampers because one would be open, one would be closed, or anywhere in between it would be proportional. So now with electronic, we're doing the same thing, but we're doing the two boxes. So what happens is, now on the constant volume ones, when I talked about that, I told you the pitot ring is down here, so it's constant volume. But on VAV, we have two pitot rings, one in front of each box, because these boxes are VAV. They can be full VAV, so it's a little bit different. Dual variable volume boxes, variable flow between the cold deck and hot deck to control room temperature. Velocity control provides pressure-independent operation for both boxes with variable flow to the room. Supplier is variable volume and variable temperature. That's a little bit different because it has both. Sound attenuators if desired, and here's what a control loop looks like for these two boxes. Whereas a constant volume one, this would go from here to here, and this one would be an X. This would do here. Well, this one is not that direction, so the programmer has the option to make the fresh air come in any way he wants. You can bring all the fresh air from the hot system, you can bring all the fresh air from the cold system, or you can do both, which I've done here. So this line here represents 50% of the minimum outside air, whatever it is. So, you know, if you needed 20% of outside air, this would be 10% from the hot deck and 10% from the cold deck. So the cold air would, when you don't need it, here it comes like this, and then we get to this 76.2, it starts cranking up until it's at full flow. It's at when it's 79 degrees in space, the cooling valve is full open, and the heating side is at the VAV box is full open, and on the heating side is open, but only to that 5% or 10, whatever it was. If it's 20%, would it be 10%? And the heating mode, when it's hot, its heating is closed or at minimum position, and then as it gets colder, it starts stroking up. So these slopes and this minimum air are completely programmable by the programmer. So he has the option to do that any way he wants to. Whatever the engineer wants anyway. The room temperature sensor modulates both the cold deck VAV damper and the hot deck damper to maintain room temperature. Minimum ventilation air should be through both the cold deck and the hot deck dampers at 50% of total minimum flow. Both dampers operate in full VAV mode for variable volume, variable temperature to the room. Typical control sequence for this, the supply fans and return fans shall run anytime the system is in the occupied mode. Modulate the supply fan speed to maintain the supply air duct pressure set point. Modulate the return fan speed to track the speed of its supply fan offset by an amount equal to the minimum outside airflow. Modulate the return air fan speed, the outside air relief, and return air dampers to maintain building pressure and ventilation flow. Modulate the chill water valve and hot water valve to maintain supply air duct temperature set points for both the cold deck and the hot deck. Reset the chill water deck supply air temperature set point based upon connected load. Every 5 minutes, if any cold deck box, I don't know why water got in there, damper is greater than 95% open and no cold deck box is less than minimum position, then lower set point 1 degrees. If no box damper is greater than 90% open and one or more boxes are at minimum position, raise the set point 1 degree. Reset ranges should be 55 to 70 degrees. Reset the hot deck supply air temperature to return air temperature every 5 minutes. If any hot deck box damper is greater than 95% open, then raise the supply air set point 1 degrees. If no hot deck box damper is greater than the 80% open and one or more hot deck dampers are at minimum position, lower the set point 1 degree. Reset range shall be 80 to 120. Now on these reset ranges, like I said, this is really simplified. When you get into the more complicated one, you don't have to use 1 degree or 2 degree. You can say in here, if we have 5 dampers at 95%, or lower or raise the temperature 2 or 3 degrees, and then you can come down at different speeds. One thing you have to be careful here with is you got to run a couple of these to make sure that your 1 degree and 1 damper open doesn't take too long. So in other words, if you had just 1 degree and it got hot quickly, it might take you an hour to get to temperature, and that's not acceptable. So you have to kind of check out the timings on this. The thought process is the same, but your numbers might actually change. Now here's the economizer, which is the same. If the outside air temperature is between 45 and 70, the outside air temperature is 10 degrees below return air temp. Now these are the same. Your climate factor will depend on what these numbers are. 10 degrees is pretty high, but the reason I like it high is because I hate for the economizer to get too close and start requiring recooling or reheating into the space. Don't like that. So I'd rather have a few less hours of economizer instead of having all this problem with those. But you can set it where you want. I live in a warm climate, so 10 degrees is more than comfortable. Some people may want this down around 4 or 5 degrees or 3 degrees, but don't get too close, because the reason is the temperature sensors can be slightly different calibration. The outside air sensor and the return air sensor might be slightly different, and if the calibrations are slightly opposite, you will cross and you actually have some reheat. So be careful with that. Monitor room temperature, room humidity, supply or duct air temperature set point. So that's the basic sequence for a VAV. The only thing that's really different is that outside air damper. You have to be careful with it. Now this one here didn't have a minimum outside air damper. And the balance guys have little problems with this sometimes because these are called low leak dampers. Low leak doesn't mean no leak. They do leak. And sometimes, if the minimums are small, these dampers will leak almost enough for your minimum outside airflow. So it's good to have that little damper, that minimum flow outside air damper is really good to have in a unit. All right, now I'm going to switch gears and talk about a specialty one. I know this is not a package units course, but it's good that you know about this. And it's called a variable volume temperature system is what it is, VVT. This is a regular package unit, and it has the same thing as other VAV units. It has a duct going out. It has VAV boxes just like anything else, but it has something different. It has a large damper or VAV box that can bypass the supply duct and put it back in the return, because this is a package unit. And a package unit cannot stand variable flow on this this coil for very long. It's got normal coils are good for about a 30% variance, and after that, you could actually damage the compressor. If liquid refrigerant starts flowing back to this compressor, it will damage it. Now, scrolls are a little bit less acceptable to that, but still, it's a problem. So now, you ask, why are we doing this? Well, years ago, when VAV came out, it was pretty expensive, and people said, I can't afford it, but I still need an area that needs to be a whole bunch of zones. So we could put this system in for very little money and still do the job, but with a package unit. What this does basically is this right here has a velocitrol. If we look at the control system, we have a velocitrol right here, which watches the velocity of the return duct. And what it does is it modulates this damper to keep it constant. So this is asking for constant velocity of the return, which means it's constant volume. And so these can take all the air they need, and this will sense it by the velocity changing, and it will change the damper position. These actually work pretty well. So you can dial this in really good. And of course, other than that, it's a standard VAV, except these boxes down here, this unit has a little bit of a problem, and that is that this is a package unit, so it's got heating. Well, this happens to be a heat pump, but it could cool or it could heat. And that means these boxes have to be able to reverse actions. So if the box is a cooling box and the room is hot, it needs more air, it opens the damper. But if it's in heating mode and the room gets hot, it wants less air. So it has to work in opposites. So you have to have a system that can send a signal out to these to tell them, okay, you're now a heating box, not a cooling box. That's the only problem. So these are pretty simple. The supply fan should run and the outside air damper should be open anytime the unit's in occupied mode. Modulate the unit bypass damper to maintain a constant velocity at the velocity sensor. Stage a compressor and strip heater to maintain a supply air duct temperature set point. Reset the supply air temperature set point every 5 minutes. Monitor all VAV box damper positions. If in cooling mode, if any damper is full open and no damper is at minimum position, decrease the supply air set point 1 degree. If no damper is full open and one no more at minimum position, increase the supply air set point 1 degree, right? We're in cooling. Reset range should be 55 to 70 degrees. Now these here also can have reheaters on them if you need them. Typical control sequence in the heating mode. If any damper is full open and no damper is at minimum position, increase the supply air set point 1 degrees. No damper is full open and one or more dampers at minimum position, decrease the supply air set point 1 degrees. Reset the range should be from 70 to 95. Monitor room temperature, room humidity, supply air duct air temperature, supply and refrigerator fan status. Now these are simple systems on a package unit, and you have to have this bypass damper on them. Okay, this is a control operation of parallel air handlers. Now this is a little unique, and the reason I'm talking about these have a special problem. If you run into these, you need to know about this problem. So parallel air handlers are one where they're staging these air handlers, where this one may be stage 1, this may be stage 2, or one may, maybe they run up in capacity together because maybe there wasn't space big enough for big air handlers. They put 2 smaller air handlers in the space. And this is a typical way that you'll see these, where they'll have a controller for this system and a controller for this system, and they have a supply air, a pressure sensor for this one, and a pressure sensor for this one. And they'll have VFDs. And this looks okay, but it has a problem. Used for stage, like I said, are large floor quantities for smaller air handling units. Operation failed. This was the first job I ever did like this. I thought, well, this was cool, but operation failed due to windup. Now, what windup is when you have some sensor variability where you have, let me just go through this. So if you have this situation with these 2 pressure sensors running these 2 fans, if this system is 1 second slower than this system, then when you come back the next day, this won't be doing the full load and this one will be doing 0 load. What happens is, just think about it for a second. If this is pressure controlled, and all of a sudden this one sees that it sees it first, that this duct needs more air, it will speed this fan up. Well, as this starts to speed up, this one says, well, I need a little more. So it starts speeding up. But this one, if it speeds up faster, it will finally make the pressure, and this one will just back down. It's, oh, I've already got pressure. I don't need pressure. It'll back down. And that discrepancy will eventually drive apart. When we had this job, we set them up. Hey, this is beautiful. Let's go home for the day. And we go home for the day, come back the next morning. This one's doing all the load. This one's just coasting a minimum. What the heck? We did it a couple of times and finally figured out you can't do it this way. There's no way you can, we tried fine tuning it. It's just not going to work. So what you have to do to make this work is you had to retrofit the system so that there's only one controller. Now you could have, a controller for this air handler, a controller for this air handler, but you can only have one pressure sensor. So you had to run the pressure sensor to one controller and then have it drive both VFDs. Or you could have this one reset this one. The only problem with that reset this one is there is some latency in that lag, which is a problem. So basically you need one controller running both these fans, and then they work perfect, no problem. By the way, loop ducts are also parallel fans. right? So, just because they're on different sides of the building, and the same thing, loop duct units have the same issue as this and require that one sensor. Now, it's a little bit harder in a loop duct, as I've done loop duct jobs where the engineer put dampers here, automatic dampers, so if he had to, he could close these dampers and just run one unit to keep one side of the building totally cool, or you can close this damper and have one unit run the whole floor. A little bit more complicated, but remember, if you have dampers here, then you have to have more than one pressure sensor. If you put one pressure sensor in and close the dampers, you can't run this air handler. So what we've had to do in those situations is put two pressure sensors, but only have one do both units and have the other one communicate with that one. It's a little complicated, but you must have only one pressure sensor. So the typical sequence for these are the air handler should run anytime the system is in the occupied mode, modulate the supply fans speed to maintain each supply air duct pressure set point, but remember there's only going to be one. If the supply air static pressure set point is not achieved in 2 minutes, start the second air handler and modulate the fan speed to maintain the supply air pressure. If the fan speed drops below 30%, stop air handler 2. Okay, that's just a basic sequence. All right, so now we're going to talk about outside air systems. So this is an energy recovery unit, and this is a really simple deal. So you've got some exhaust fans in the building, or else this is the exhaust fan of the building, and it sucks air from those exhaust loads this way, and then we have an outside air load that comes in this way and goes to the makeup air units, the other units. So these normally don't do cooling or heating directly. They're actually feeding other units. The control system has a starter here and a starter here, and sensor switches to tell where they're at. It has a temperature sensor on the exhaust inlet, a temperature sensor on the fresh air outlet, and a temperature on the outside air inlet. So what happens, this outside air comes in, and this exhaust air transfers its temperature or energy to the fresh air. So in the summer mode, it will take and this air is hot, this air will cool that air down. In the winter mode, it will heat this air up. So what we're doing is taking energy out of the exhaust and moving it to makeup air. These are normally less than 70% efficient, but you can get up to 70%. This particular one is showing a air-to-air heat exchanger, which is a fixed heat exchanger. And the good thing about this keeps the two air streams completely separate. So in case you have any contaminants in this stream, it can't transfer to the incoming air. So its sequence is pretty easy. Exhaust and outside air fan should be on, and the outside air and exhaust air damper open when the unit schedule is in the occupied mode. Monitor the outside air inlet and the outlet temperature, exhaust inlet temperature, and fan status for both fans. All right, so now on this unit, on this sequence, what happens is it looks at it's on and running. And when we want to know what energy, we just watch these. This sensor and this sensor will tell you how much energy is being added or subtracted. So that's what those sensors are for. A DOAS unit, which stands for a dedicated outside air handling unit. So it's basically a makeup air unit. It has an isolation damper. It has filters. It will have coils. It can have more than one, of course. You can have preheat, you can have cooling, and it can have a heating coil. And normally they have these two because these units are actually supplying air to other systems, other air handler systems. And the reason they use DOAS, if you want to have dehumidification control, if you want to have a lot of cold, or you got a big outside air load, or you have a very large temperature outside, either cold or hot, that you need to make up, you can actually save money by putting all that sophistication in one outside air unit and have the other air handlers just be air handlers that are getting their outside air is tempered already. So it can take some of the load out of those air handlers and move it into this air handler. So it can be an economic choice. It's also a good maintenance choice because all the difficult maintenance is here. These here are much simpler maintenance down here. So here's the supply duct, and it goes out to fresh air dampers on other air handler systems. Of course, it has a control system. It has these are variable volume, so it has a pressure sensor here. And as the flow changes down here for fresh air, then this system can speed up and slow down for that. So the sequence is, the supply fan shall run and the outside air damper shall be open anytime the system is in the occupied mode. Modulate the supply fan speed to maintain the supply duct pressure set point. Reset the supply duct pressure set point to maintain a room pressure set point. So remember, this system is actually pressurizing the space. Modulate the chill water valve and hot water valve to maintain supply air temperature set point of 80 degrees. Reset supply air temperature set point to equal average return air of all connected units. So basically, we're gonna reset this temperature. It starts at 80, but we want this to be equal to the return air of the other units. So basically, we're taking out any outside air load at all from these systems. Modulate the pre-hot water valve, the preheat hot water valve to maintain the outlet temperature of the preheat coil of 45 degrees. If the room humidity rises above 60%, start the dehumidification mode. In dehumidification mode, control the chill water valve to maintain the room humidity set point of 50% room humidity. Modulate the hot water valve to maintain the supply air duct temperature set point. If the room humidity drops below 48%, disable dehumidification mode. Standard dehumidification sequence like the other ones. Monitor the supply air temperature, room humidity, and supply air status. So this is basically a DOAS unit. Now we have a makeup air handling unit, which is similar, except normally is just a single load. So normal, this has a heating coil and a cooling coil. Most makeup airs don't dehumidify, just a straight unit. And of course, it goes down to a unit or a space. Could be makeup for a kitchen hood. It might be makeup for fume hoods. It might be general makeup. Don't know. So this control system is really simple. It has a fan, start, stop. Normally these are constant volume. There's a cooling coil and a heating coil, so it's got valves. It's got a supply air temperature sensor. So the supply fan shall run and the outside air damper shall be open anytime the system is in the occupied mode or commanded on by a user. So if this was a kitchen hood, the cooks or chef will turn on the fan. So this is, I'm calling this an outside air damper, but it's actually an isolation damper because it's as big as a unit. Modulate the chill water valve and hot water valve to maintain the supply air duct temperature set point. It shall be operator adjusted and the set point should be 75 degrees because it's makeup air, but they can adjust that temperature. Monitor the room temperature, supply, and supply fan status. It's a pretty simple unit, makeup air units. This is called an energy recovery unit, air handling unit. It's a little more complicated and normally much larger. So these are used on spaces that have a whole bunch of outside air. So what you have here is an air handler here. These are plug fans, of course. And we draw in through the filters. And this one is using a heat wheel and then into a cooling coil and heating coil and back to the space. And then this side has return and exhaust air from the space come and hit the wheel and go out, and it's exhausted. So these are 100% outside air. So all the air is fresh air coming in the system, and then we transfer the heat from the return air to the supply air. These can get really complicated. It's a simple concept, but they can get complicated. And of course, it has coil valves for the coils. It has the duct that runs out, and this is just like the DOAS unit. It runs out and supplies other units. Or I have seen this used for huge zones, like an auditorium or something, where you don't need boxes, you just need a whole bunch of air for the space. This could be cooling and heating of one zone, but normally they're used for makeup air for other systems. And the control system is the same, normally a bigger unit because they got VFD on these fans, VFD on these fans. This one's got enthalpy based, so it's got temperature and humidity on this side, temperature and humidity here, and temperature here. So we can tell what the enthalpy change of this wheel is with these. We have a supply air duct pressure set point. We have valve control, and we have a humidity sensor here in the mixed air. So we got all kinds of positions. We can tell what's going on with this system. So the supply and exhaust fan shall run and the isolation damper open anytime the system is in the occupied mode. Modulate the chill water valve and hot water valve to maintain supply duct temperature set point of 80 degrees. Reset the average return air temperature of the connected air handling units. So this sequence here is assuming that these are feeding other air handlers. This is feeding a room. This would actually be a room temperature, which would be different. Modulate the supply fan speeds to maintain the supply duct pressure set point of 1.5 inches or whatever set by the tab contractor. Modulate the exhaust fan speed to track the supply fan speed minus a differential to provide the correct outside air quantity to provide building pressure set point of 0.02 inches. And now we're going to some resets. If during summer operation the outside air enthalpy is 4 BTU per pound greater than the return air enthalpy, then close the enthalpy wheel bypass dampers and start the wheel rotation. If the differential enthalpy drops to 2 degrees or less, then the wheel and stop the wheel and open the bypass dampers. So this wheel has bypass dampers, and these bypass dampers are basically to relieve the pressure. So there's still air going through the wheel, but we've got it bypass, so we're relieving pressure to save some energy. During the operation, the outside air enthalpy is 4 BTU per pound less than the return air enthalpy, then close the enthalpy wheel, bypass dampers, and start the wheel op rotation. The differential enthalpy drops to 2 or less, wheel and open the bypass damper. So basically, it's not an economizer, of course. We're just starting this enthalpy wheel if there's energy to be captured. You know, if these are two of the same temperature, there's no energy to be captured, we won't start the wheel. A couple of clever things about heat wheels. The heat wheels come in 2 types, dry bulb and enthalpy type. A dry bulb it's just an aluminum mesh screen or a brass mesh screen, and it transfers the heat, or it could be a brass screen that has desiccant attached to it, and that'll absorb moisture, so it'll actually change moisture. But interesting about these wheels is direction of flow is important. You must have opposite flow. So if this one's flowing this way, this one's got to flow this way. And the reason for it is if this one has some, let's say this one coming from space has some lint on it, gets through these filters, and it impinges on this wheel. If this one went the same way, then it would just try to push that lint further in the wheel. But since it's going this way, it'll actually push that lint off. So that's really important because these can get impacted, and if they do, there's somewhat of a problem. The other problem is if it's an enthalpy wheel, it's got desiccant on it. If they get absorbed they get wet, they get totally wet, they have to be dried out. And either they have to be heated up with hot air, or else you have to take the wheel out and recuperate the desiccant. It's kind of expensive, but that can happen. This is a dehumidification mode. So if the room humidity rises above 6%, place it in dehumidification mode just like the others, so we can drop this cooling coil down to 55 degrees and let it dehumidify the air by dropping moisture out. And this coil comes up and turns on the temperature to keep the temperature set point the same so we don't freeze out those spaces. Monitor the supply air temp, return air temp, outside air temp, mixed air temp, return humidity, outside air humidity supply, and exhaust fans status, and wheel status. So we got a lot of points on these systems. And that's it. You made it to the end of VAV and outside air units. I hope that was beneficial. If you're not already a subscriber, become a subscriber. I really appreciate it. And I do appreciate you watching these videos. If you have any comments, put them down in the section, and I will be sure to answer them. You guys have a great day, and I'll catch you on the next one.